Hello. Today we are continuing graphing. In section 3 we graphed reciprocal functions, which are really basic rational functions that might look like this or something like that. Today we're going to graph more general rational functions, and we're going to talk again about vertical and horizontal asymptotes. And we're also going to talk about oblique asymptotes and point discontinuity. So those are the 4 things you should look out for in this section. And there's a bunch of new vocabulary that will come up, so by the end of this section, make sure you can talk about what each of those things are. To start out with vertical and horizontal asymptotes, we're just going to talk about rational functions. Rational functions look like f of x equals a of x over b of x, so a polynomial divided by a polynomial. And obviously b of x cannot equal 0 because it's in the denominator. If I want to graph a rational function, there's 2 things I usually want to find, the zeros and the asymptotes. And then from there, it will tell me where I can plug in x's into my table of values. The 0, remember the 0 is the same as the x-intercept. It's the point where y equals 0. The 0 of a rational function happens where a of x, which is the numerator, is equal to 0. So to find the zeros of a function, we set the of a rational function, we set the numerator equal to 0. Vertical asymptotes happen where the denominator is equal to 0. Remember, the equation of a vertical asymptote will be x equals a number. So wherever the denominator is equal to 0, I have a vertical asymptote. And then we have some rules here for horizontal asymptotes. So again, here is my rational function. Notice they say no common factors other than 1, so that means we should factor and reduce, or make sure that we simplify our rational functions. Vertical asymptotes happen where the denominator is equal to 0. It can have one horizontal asymptote, and there are 3 rules for how to figure that out. If the degree of a of x, which is the numerator, if the degree of the numerator is greater than the degree of the denominator, we have no horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, then it's y equals 0, which is the x-axis. That's my horizontal asymptote. And if the degrees are equal in the numerator and the denominator, we just take the leading coefficients of the numerator and denominator, and those make my horizontal asymptote. So let's look at these pictures down here. X squared over x plus 1, that goes with the first case, no horizontal asymptote. There's a vertical asymptote where the denominator is equal to 0 at x equals -1. The second case here, we have one horizontal asymptote at at y equals 0, right? So here, notice that the degree of the denominator is greater than the degree of the numerator. The numerator is less than the degree of the denominator. So the x-axis is our horizontal asymptote. My denominator here is x minus 1 times x plus 1. So -1 and +1 make this 0. That's why I have 2 vertical asymptotes at -1 and +1. And here I have my third case, where I have a horizontal asymptote. Notice here the degree of the numerator is 1 and the degree of the denominator is 1. They're equal. So I take the leading coefficients, meaning the coefficients of those terms, which is 2 over 1, and that gives me my horizontal asymptote. My horizontal asymptote is here at y equals 2. And my vertical asymptote is where the denominator equals 0 at x equals 3. All right, so let's take a look at this graph. This particular graph has no horizontal asymptote, which we'll see in just a second. So step 1 is to find the zeros. To find the zeros, we set the numerator equal to 0. So in this case, my numerator is x cubed. When I set that equal to 0 and take the cube root, I get x equals 0. So the point 0, 0 is the x-intercept of the function. Now we're going to check out our asymptotes. For vertical asymptotes, I set my denominator equal to 0. So x plus 1 equals 0, which means x equals -1. That's my vertical asymptote. In this case, there is no horizontal asymptote. Remember, my function looks like this, x cubed over x plus 1. the degree of my numerator is greater. The degree of my numerator is 3. The degree of my denominator is 1. No horizontal asymptote. So for step 3, basically what we do is we use a table to get ordered pairs around our asymptotes, right? So we know there's an asymptote at x equals -1, right? So that would be undefined. So I'm going to pick some x values on either side of that and plug into a table of values, and I get this weird looking graph. So here is my line x equals -1. That's my vertical asymptote. There's no horizontal asymptote. To get the rest of this graph, I just plot the points that you got from this table of values. And you would use a calculator probably to help you with some of these decimal numbers over here. All right, so I want you guys to try that with this graph. Okay, hopefully on your notes you followed the steps and you found the zeros and the asymptotes and then did a table. So step 1 is to find the zeros. We end up with the point 0, 0 right here. And then I find my asymptotes. My vertical asymptote comes from setting the denominator equal to 0, so I get x equals 1/2, which you can see with that dotted line right there. And then since the degree of the numerator is larger than the degree of the denominator, there's no horizontal asymptote. I'm not going to show you the whole table of values right now. I just want to show you my thinking of how I set it up. I always think about where my x values are undefined. So in this case, x equals 1/2 is undefined. And I make sure I pick some x values on both sides of that. So I make sure I show both parts of the graph. All right, next we are going to talk about something called oblique asymptotes. Oblique asymptotes are basically diagonal asymptotes, or asymptotes that are not vertical or horizontal. They look like diagonal. So if I have a rational function where I've taken out my common factors, f of x has an oblique asymptote if the degree of a of x, which is the degree of the numerator, minus the degree of b of x, which is the degree of the denominator, equals 1. So if the difference between the numerator and denominator is 1 as far as the degrees go, it has an oblique asymptote. And we get the asymptote by doing a of x divided by b of x. So I do the numerator divided by the denominator, and this is going to require long division. Notice it says with no remainder. So I do my long division, I ignore the remainder. Whatever I get as my quotient without the remainder is the equation of my oblique asymptote, which I'll show you in the next example. So if we look here, if I take the degree of my numerator, which is 4, minus the degree of my denominator, which is 3, I get 1. That means there has to be an oblique asymptote. In this case, it's x plus 3. The vertical asymptote is still wherever the denominator is equal to 0. So what makes x cubed minus 1 equal to 0? X equals 1. So here, x equals 1. This is my vertical asymptote. Here I have the line y equals x plus 3. That's my oblique asymptote. And my graph looks like this. So let's do an example. Figuring out oblique asymptotes. So step 1 again, this is a rational function. We're going to find the zeros. So set the numerator equal to 0 to find the zeros, and I get x equals 0. So there's a 0 at x equals 0. That means the point 0, 0 is on my graph. Find the asymptotes. Again, set the denominator equal to 0 to get the vertical asymptote. So there's a vertical asymptote at x equals -1. Remember, my function is x squared over x plus 1. Now to get my other asymptote, I look at the degree. The degree of the numerator is larger than the degree of the denominator, so there's no horizontal asymptote. And the difference is 1. 2 minus 1 is 1, so there is an oblique asymptote. How do we get the oblique asymptote? We divide the numerator by the denominator. Remember, when I do long division, I have to fill in my missing terms with zeros, so I'm doing x squared divided by x plus 1. How do I do this? I say, okay, x squared divided by x. Let me erase this for you. X squared divided by x is x. Then I take x times x plus 1, which is x squared plus x. I subtract that whole thing. X squared minus x squared cancels to 0. 0x minus x is -1x. Bring down the 0. Now I do the same thing. Negative x divided by x, that gives me -1. -1 times x plus 1 is -x minus 1. I subtract that. Negative x minus negative x is 0. 0 minus negative 1 is 1. This one is my remainder, but remember, for an oblique asymptote, I don't need my remainder, okay? The equation of my oblique asymptote is just y equals x minus 1. It's this quotient that I get here without the remainder. So I'm going to draw in my asymptotes. So here I have the line y equals x minus 1, which we got back here, right? Y equals x minus 1 is my oblique asymptote. So a y-intercept of negative 1 and a slope of 1. My vertical asymptote is negative 1. And then I would use a table of values to graph my function. So x is not defined at negative 1. I would pick some values on both sides of negative 1 to make sure that I get enough points on my graph. All right, here's one for you guys to try. All right, the answer here is B. You should have gotten the vertical asymptote by setting the denominator equal to 0. So x equals 4. That's where it's undefined. To get the oblique asymptote, we do long division. This is what your long division process should look like. We get a remainder of negative 6, but remember our oblique asymptote is our quotient, x plus 1, without the remainder. So y equals x plus 1. Y-intercept of 1, slope of 1 is my oblique asymptote. X equals 4 is my vertical asymptote. And then you should have used a table of values with x values on either side of 4 to get the shape. All right, last but not least in this section, we have something called point discontinuity. Remember, up until now, we've been saying that our rational function is a of x over b of x, and they have no common factors except 1. So what happens if there is a common factor? When there is a common factor, we have something called point discontinuity, or another way to say it is a hole in the graph. So let's take a look at this graph. Here we have x plus 2 times x plus 1 all over x plus 1. If I simplify like I did in the first section, the x plus 1s cancel out to 1, right? That gives me 1 over 1. And my function just looks like f of x equals x plus 2. But just because I canceled those out doesn't mean that that discontinuity goes away, right? My denominator is x plus 1, and at x equals negative 1, that still can't happen. I can't plug in negative 1. It would still make my original function discontinuous or undefined. But if it cancels, if that discontinuity cancels, if that common factor cancels, then instead of being an asymptote, if it cancels, it makes a hole. So this is where x equals negative 1, right? So wherever x equals negative 1 on the graph, I just show a little hole. It's not an asymptote, it's just a hole, because my new graph looks like this. F of x equals x plus 2. Y-intercept of 2, slope of positive 1. But wherever x would be negative 1, my graph is not defined, so that looks like a hole in the graph. Let's look at this example. X squared minus 4 over x minus 2. I should always factor to see if there's anything I can cancel out. In this case, when I factor, I get x plus 2 times x minus 2 over x minus 2. X minus 2 cancels, and I'm just left with x plus 2. So the graph of my original function looks like the graph of x plus 2, but at positive 2, where my denominator would equal 0, instead of being an asymptote, it is a hole. So there's still a problem where my denominator equals 0, but it's a hole because it cancels out. So when I graph, right, again, I'm graphing the function that looks like x plus 2, y-intercept of 2, slope of positive 1. But wherever x equals 2, wherever it would be on my graph, I have a hole. It is undefined there. All right, so I want you guys to try this one. It's a very similar example. All right, the answer here is C. If you notice, when I factor this, I get x minus 4 times x plus 4 all over x plus 4. My x plus 4s divide out to 1, so I'm just left with x minus 4. So my graph looks like a straight line with a y-intercept of negative 4 and a slope of positive 1. But my denominator, x plus 4, the problem is it would equal 0 at x equals negative 4. So wherever x equals negative 4, at negative 4, negative 8, there is a hole in my graph. So instead of an asymptote, if it crosses out, I have a hole. So things you should be able to remember from this section: vertical asymptotes, horizontal asymptotes, oblique asymptotes, and holes, which are also called point discontinuity.